We're gonna look into a function called surface morphing in Grasshopper, and that actually is a name for several different methods you can use. That means that you place geometry onto a doubly curved surface or non-developable surface like this. That is very similar to what's already existing in Rhinoceros called flow along surface, which is a very accurate and good command. But it's not really parametrically manageable in Grasshopper previously, at least in the same way, but now it is through surface morphing and another function called SPLOP, and we'll show you that later on here. So this is the function. I'll show you first how to do this in Rhino, so flow along surface. If you see here up here I'm typing, and also like in the input objects in Grasshopper actually corresponds to the command line up here. So it's going to ask you questions and then you're going to simply answer them. So flow along surface, a question comes, select objects to flow along a surface. Now we'll take all these pyramids that I made here. You see they look like this. And they are joined into one surface, so I click them. And then I'm supposed to press enter when I'm done, which I do by clicking right click on the mouse button or the enter button. And then base surface. So this is more or less a reference surface to be mimicked. Select edge near a corner. And you see here there's a lot of, well, there are some settings you can do. Preserve structure, no, for example, rigid, no, and so forth. This is not really directly visually applicable like it is in Grasshopper, of course. So base surface, select near a corner. I have this blue one here, that's my reference surface. Click in the corner. And then it asks target surface. Select edge near matching corner. Matching corner, that means if I click somewhere on this corner, on the blue one, it should be somewhere around here then on the cyan one. So I click there. And almost immediately something happens. In this case, they're actually on the other side of the structure. These things then happen, and this is something you can then effect in Grasshopper. Although this operation went very well, of course, as you see here. So you see I can take away this and look at this in rendered mode. They're open in the backside, but you see the curves are absolutely perfect all over the place here, so they actually mimic the surface side, the target surface perfectly. And then they twist all the pyramids on the other side like this. Then of course one can develop that so that it gets the other way around, but how can you control that a little bit more accurately? So now we have here the same structure made in Grasshopper, and you know, that's I can, like, for example, lower or higher the pyramids like this. And you see that it goes not so fast right now, but it's because it's attached already to 3 different methods. So what you see here is actually quite fast, given that they're actually doing this in real time on these. So I have 3 sets of methods right here. First we have which one is it? It is the sporf. That is a surface point morph. And as you can see, this function or this component creates something which is very similar to what we just saw up here. But we could control the back, what's in front and what's in the back on this surface morph in Grasshopper. I'll show you that later on. And then we have the surface morph here. This is a surface point morph, and here's a surface morph. What is the difference there? Well, you can then spread it and stretch it across the surface in this manner. And you can also affect the W input, which is the U and V input, the domains of the surface, and then you also have the W coordinates, which is then you can describe it as the Z plane, the Z direction of a plane. So you can stretch them back and forth in this, and actually then affect an extrusion afterwards. So this is not affecting the initial geometry that we had. So you can spread that out, so you then have a little more control. So that actually, it depends on what geometry you're working with, certainly. And then we also have something called splop, this one, which is a quite funny name indeed. What does that do? Well, you see it's actually a bit outside of the surface here. It's actually trying to maintain the original geometry as far as possible. And then you can also rotate it around on the surface. You see here that the surface is obviously a little bit too small. So we could, for example, increase it like this. And then it's obvious that we need to reposition where this geometry is positioned. So, for example, we can extract a center point here and use that instead for the positioning, simply like this. And this is the interesting part where you can actually sweep it around the surface and it will adjust accordingly. So this is a rotation device put in, and then imagine that you would have very many pyramids, like maybe the double in each direction. Then of course maybe you can see already how you can use this. It means that you can actually adopt the properties of the surface onto this geometry. And it's actually not so much distorted either. So it's this splop version here. It tries to maintain the original design as much as possible. So if you compare to these instead, here it's then automatically also increased. You see that they are actually getting more compact. You transform the pattern in a completely different manner. So it has to do with what you want to do with your design, actually. So depending on what you design, you have to try these, or if you already know these three methods or components, you will be able to choose the right and most suitable method for your project. Okay, so let's build this then from scratch. So we'll start with building a pattern. So we go to vector and to square grid in this case. You can actually do whatever shape you want to. So I'm just gonna do a quite quick one now. So I'm gonna leave the S on 1. It's 1 on default, as you might know, and I'm taking maybe 10 as max. By the way, you can also, I'm going to lift the middle point now, and you can also do this in a random manner, of course, with a random device, if that's interesting for you. I'm going to do all of the pyramids the same height, just for showing this, because we're going to show surface morphing actually. So, and then I'm going to move this. You saw I took the area, I took the center of the cells, and I'm moving the cell upwards at a specific parameter, maybe from 0 to 1 or something like this, might be enough for this test. And then I'll do an extrude point. See Google there, it's situated here on surface freeform. So then that is practically making a base, and then extrude that base as a surface to a point, and then you have all the pyramids already. So mind you, if you count all of these cells, how many they are 100, with a list item, list length, I mean, like this. You can use this and flatten it. You can use this number, it would change of course if you do this, and then you have something else. I will leave this as 5 now. So this can be put into a random number generator, then affect, and which then comes in here to affect the height so that they're always and randomly high. In this case, I'm just going to leave it like this. And we need, of course, as I showed before, we need to have a reference surface and we need to have a target surface. And a reference surface, we've shown that a couple of times before. Bounding box, and I can simply put that, if I want to have a surface, I will put them around the cells, the original cells, like this, flatten it, and go right click to union box, and then you can hover over the first B output and set flat box. That's actually a quite perfect reference surface. In some cases we actually need also a reference box. And that's the same component. I mean, this makes a flat surface simply because the cells here are all flat, right? If you want to have a box, we should put this box around something that has also geometry that has parameters in the Z direction, like the pyramids, for example. So if I simply copy that and take it to the extrusions, I can put them next to each other like this. Now I know this is the surface I need, and this is the box I need. We can actually simply hide them now. We don't need them. No, we don't need to see them. We definitely need them to continue with the different surface morphing procedures. So what we need more is a doubly curved surface or some complex surface that you make. I already prepared these curves. I'm going to use these curves. So I'm imagining that this is the section curves, these two, and this is a rail, and then I can make a sweep curve, a sweep surface from that. So, but of course you can create a surface in many other ways, but this is just an example. So I type sweep, and I need a rail. Set one curve, this one. You see now that I'm actually I'm not taking a component. I'm just taking directly in from the sweep command itself. Yeah, like that. And then if I move these, the surface is going to be changed as well, which is quite good. So here is my surface. I inserted the curves directly here by right-clicking. That's also possible. Sometimes one can do like this as well, and because then you see which curve is which curve, so to say, immediately by clicking on the component. But now I did it like this. Okay, so this is our target surface. So let's see if we can then first locate these on morph. We're talking about sporf, surface morph, and splop. It's quite funny names, I know. But the first one is it's called like this, surface morph by point. So the P is like stands for a point, actually, as far as I'm informed. If we open that one, you see what I mean. So the geometry that we're gonna transform, that is of course the extruded pyramids. These are now open surfaces, by the way. You can also make this as a closed surface. It has the same effect if these were to be poly surfaces. Now they're open surfaces, but it's exactly the same procedure and will work also with probably a little bit more effort from the computer if it's a closed poly surface. And then we hover the next one here, the base surface that we already have. Well, now we can actually I would rename this so we don't have to see it the whole time. So if you right click and I type ref surface, then I know which one it is. And I type here as well ref box. And then I do with just right clicking on the component. Now I can unhide that one. So the first output, that is a flat box. That's precisely what we need. So that is goes into the first one here. That's a base surface. Then we have a UV parameter on the base surface used for orienting. this is of course pretty crucial. And when it says UV parameter, you can't just use any point. It has to be attached to the surface somehow. And usually, I mean, if I then now go to area and attach that flat box to it, I get a point, definitely. It is on the surface that we know, because it is a flat surface on XY plane. But to be absolutely sure, one should create a UV point surface, a surface UV point. So if you go to surface and analysis, it's already here actually, but it's this surface closest point. How can you find that? Well, if you start searching for UV point, or parameter on surface, maybe on the internet, or even here, or the closest points, it will come somehow, until you will find it. I'm pretty sure. The more you search for something like that that has a UV point output, you will find it. And that I'm saying that just as a comparison to other components in different examples. So the search function in Grasshopper is actually pretty good. So that's how I found it once. So if you hover on this one, on the title, you will see what it makes. Find the closest point on a surface. And you see on the output already, it will generate a UV coordinate on a surface that it's analyzing. So that's exactly what we need, because this asks for UV parameter. And we hover the first input and it says the sample point. I would say it's this one. And the surface it wants to analyze as well, and that's the reference surface. So it looks like that. And actually the whole time you have one of these UV, but there's different components where this is used as well. It's supposed to be connected in this manner. You will see later on, and with the target surface is the same thing. And then this situation gets a little bit different, because now it's more or less the same point, obviously. So you can enter the UV point there. So you see there's a line of communication here. It gets the surface, and it also gets information about a specific coordinate on that surface. And this is very good, because if we change this point, the pattern is going to be reoriented. It's going to land differently on this surface. And we continue to hover here. We see target surface. I have that here. And we also have UV parameter on the target surface. So it's the same situation. So here's a target surface. I'm going to use this target surface actually for the other components as well. So we could copy this and detach, of course, this one, and then I put that into the area command and see what it lands. And this is where the problem starts. Would you use this point, it would have, then the system would not understand what you mean, because it's not on the surface. You have to have it on the surface, but you can use this point as a guiding device, so to say, to find the UV point on the surface. And UV is like imaginary lines like this. I can show you by doing a brep wireframe and type something like 5 maybe. So these lines are the UV direction. So U, I suppose, is in this. I don't actually know which is U and V here, but I think it's like this. This is the U direction, and like this is the V direction. And then we also have something called the W direction, and this is actually from the surface to the point here. So all surfaces are described in UVW, just very much like the Euclidean space itself, X, Y, Z. So all surfaces are described in UVW, actually. So much for that. Now we will also need to find this point. We will need the surface, so we attach that to the surface closest point component, and then a new point appears, and that's the closest point on the surface from the reference point we used. Sounds complex, but it's actually not really. That means that this point that we made here and this point, this is gonna be the middle of the placement now. But mind you, we might have to change that. We don't really know if it's gonna land correctly or not, and we don't know which one, how this surface is constructed currently. One can analyze it, but it's easier to just try it out, because if the W direction is towards the red point here, then the pyramid is going to be this direction, but it's on the other side and it's going to be on this direction. So we'll see. The UV point goes in there, and then the target surface goes in here, and it goes pretty fast as well, actually. So it's already there. And now you see what happened. Now they're on the back side. So the question is, how can you actually change that? Well, you can change UV point. For example, it might not be such a good idea to have it in the middle. Maybe you want to have the corner point instead, like this point, and use that as corner point also. So then you can swap. So I show you, for example, how you can swap that. So if I type like here is 0, 0, 0, so it's pretty easy. I can simply construct a point which is 0 on all of these on beforehand. So you see it's there. Then I can use that instead for the reference surface. So I can skip this one and simply put that point instead. And then I need to have this, right? This edge. Then I can type, for example, control points. There's many ways of doing it. I can take that out. And then there's a lot of control points, of course. But we take a list item and pick the point which is in the corner. You see there are 4 corners actually and a lot of control points. So list, no, not list, sorry. List item. Take that in. And let's see, which one is it? It's only 1 point. Ah, it's up on the corner. Well, one can try. And then I put that in instead, and that worked actually immediately. Well, you can imagine what just happened. I mean, you have to then pick the specific point that you want to have. Now I have a very uniform pattern. So well, what is back and what is in the front, it doesn't really matter in this case. So I can take out these, and yeah. Then you can of course also search for a new point. If I type, for example, instead here 1, oh, whoops, now I have number 0, and I type 1, nothing really happened. You see, you can go on there and try to find the right point, and then things will change like that. For example, now it went back again. So the UV point actually controls how the surface is supposed, or the 3D parts that you made here, how they're going to land on the surface. Yes, so that's the sporf command, and then we also have something called surface morph, which is quite similar but yet a bit different. So we can use this one again. Then I will just move it to the right like I did in my preview, and with an X component here. I don't know really how far this goes. I can go to Rhino space and simply measure here. Let's see, 11, something like that. Okay, I can copy this one. I know this is 10. So now I have a slider from 0 to 10, and I move that one like this. Yes, so now we can make a similar procedure. We just have to hover on this component to see what's going on. So the first one is, of course, the geometry that we want to move, which is this one. And then we have a reference box. So now you see why I made a box. That was maybe a bit unclear before. But this component works with U, V, and W components. So, but I come to that. So this is a box. We need a 3D reference for it. We can unhide here, so that we see we'll see that it actually has more information on a flat surface, right? We have a spatial construction here, X, Y, and Z information. We can unhide that, but that's what we need, so we put that into the R in the reference box. And then we have the surface to map onto, which is not that one, but the moved one, this one. And now it gets a little bit interesting then. Then this is the difference, more or less. Here, a surface control point and UV point, that's not used. It's all based on UV and W components or parameters. So U and V, I already told you that I can look at the wireframe box again here. Just show it like this. So this is then the division of the surface, and we're not going to see it. I just divided it actually, so it's at 5, so it's 5 on each side, you see. So now the UV values are 5, 5. It's kind of like a chess, board of chess, but very deformed. And we can set that here as well with sliders then. We will go to maybe, I don't know, let's do 5 and 5 and put that in like this. But then we also have another component. We can pull it up a little bit higher than 1 here. We also have the W component, which is something that we don't see now, but you can imagine this becomes a box. Then it communicates with the reference box. This contains already information about, this is the Z direction, which will then communicate with the W direction, the properties of the surface. So if we put that in here, that's the last info it needs. It looks like that. It actually stretches it and even more. So this is like a scale, it's been scaled by 1.4, but even more actually. So you can imagine that these are almost 1.5 components of the W direction. So this should be very low, of course, to resemble the pattern that you made on the other side. And then we only stretch actually. Funny enough, it looks like it actually stretches exactly 1.4 here. That's just a coincidence, but that's if we actually take this out, because they are not comparable to each other, we can now tell the surface to divide itself by 1 point, maybe to 5 and 5, like that. Now it knows how much it should stretch and how large it should be. And this is of course very handy when you design complex patterns that are supposed to be spread onto equally complex surfaces. And then you can of course start to increase the U and V value. You saw already that the W value, that's a completely different story. So I take 10 here as well, and then we go up a little bit, and it actually goes even outside the surface and builds the surface as would it continue. And then of course there are quite large discrepancies going on. But this is a very handy method of mapping complex geometry, surfaces or solids. And then we also have the SPLOP version here. And then I showed you how it works already before, right? So this is very dependent on the UV parameter. Where you put that is crucial to how it's going to look like. Don't be alarmed if your tests actually look quite crazy in the beginning, because if it's placed so that the geometry lands outside of the surface, it's going to twist it quite much. So I would move now the same surface, but I moved this one, right? So if I move this, both of them will get moved. Now we'll actually share the slider so they, you see, they get moved proportionally. So now we have a new target surface, and the target surface we can already put in, right? You know where to put it. It's here. So they are actually built more or less the same. First it's the geometry, it's going to be deformed, then it's the reference, and then it's the target. It's the same here. Geometry to deform, source plane from deformation, and then we have a surface wrap geometry onto, surface to wrap geometry onto. Well, that's more or less target surface. So in this case you should actually experiment with quite many different sorts of surfaces to see how this splop command works. So one difference is there, at least. I mean, source plane of deformation, it's actually not really a surface this time. It could be a plane, whatever. So it's actually built in already, world XY, so we don't have to do anything there. It's already filled. What we have to do, of course, is to get our geometry. And like I said, the reference is already there. The surface, the target surface is already there. And then we need a point on the target surface. And we know how to do that. So we can take an area. Notice that I'm not copying that now. I'm doing it again just to show it. And here it is, surface closest point. You can also Google for it, so to say, or search for it. Surface closest point there. And then we use that point, and we use the surface, and we have generated a point on the surface. You see, it's exactly the same situation as previously. And we use that for the UV point, and already something happens. And this is, like I said, a little bit strange, isn't it? So that's obviously not really what we wanted. But before we do anything else, let's look at the rest of the components here. An angle, a rotation angle, and we also have a rigid option if we wanted to deform or not. So it says geometry will not be deformed. True or false? False. I mean, in this case we definitely want it to be deformed. Otherwise it would look like this. Which, of course, is also quite interesting, but perhaps not for this case. So false again. If you look at the angle, it's in radians. So all these mathematic formulas, they work with radians and not with degrees. This is something you can actually change if you want. If you're not used to radians, I usually use degrees instead, and then it gets recalculated inside the component itself. If you don't know what radians are, rotation angle in radians, you should look it up. It's very good to read about it. It's based on pi, more or less. So I take degrees here anyway, and I go to parameters, and I go to a slider, and I will set it from an integer from 0 to 360, so I can rotate it around the whole revolution here, 360, and then we can rotate to see what happens. And it's quite, I mean, it's quite absurd actually what happens, of course, but it's because it's outside of the surface, because we have chosen the center point. But it's still as good as a first test. So we need to do exactly like we did before here. We can use control points, and we list one item. And a reference point we don't even need here actually. So we take list item to select one of the points. Let's see which one it becomes. Well, that could work, couldn't it? This one. And we swap. Still looks very crazy, of course, but it's because of the angle. So if you rotate it back like this, then it works. But one thing is, of course, with this surface, a little bit strange. It's more interesting to see how splop works if you have a larger surface. So I can scale the surface instead here. If I double click and type scale, And this is the surface I want to scale, and then I want to have a center of scaling. You see, otherwise it scales from 0, 0, 0, which is there. I need that center point, and I need definitely a much higher value than preset, because preset is 0.5, so maybe something like that, like 7. Yes, and then we can, I mean, it would probably work with this point here, but I mean, to be absolutely correct, we have to swap the surface like this, and also swap the target surface. And then we have a completely different situation. Because then, to have it in the center would make much sense. So I hope I'm not confusing you, but this is usually how it's made when you're sketching your way to place things. So now I took the scaled surface, made a center point of it, and using that as a point instead. And then we have something completely different. I can scale down a little bit. And then when we turn around, we see very interesting things happen. You actually wrap it on the surface, more or less. I mean, this is, of course, very handy if you want to be sure to place your geometries in the correct position. In this case, I would also very much like to increase the size, because then we will see definitely what's going on. So the whole geometry takes the shape of the surface, which is exactly what we need, and we can test that by letting it rotate around like this. You can even place it like that if you want to. The first surface looks a little bit strange there. I can hide it out. And then, certainly, if you want to change the appearance of the surface, that works too. Maybe you want to do something like this. Take that one. So you see it goes pretty fast as well, which is great. Yes, so this was a small overview of the surface morph command, or how to reposition and map not only curves but actual surfaces and solids onto doubly curved surfaces or other complex surfaces.